Okay, let's get started. So welcome to the oral session on recognition, detection, and re-identification. So we have 19 papers here. As usual, they will be arranged in groups of 3, 5 minutes each. First of all, if all the speakers could please come to the front 2 rows so we can make sure that you're here if you're not there already, please. Also, I need to remind you about asking questions. So remember, you can go to slido, sli.do, and use the hashtag ICCV19_D1 to ask questions, and please ask questions. All right, and with that, I think we can get started with our first speaker.
Hi, my name is Sayna. I'm a PhD student at UC Berkeley, advised by Professor Darrell. Today, I'll present our work on active learning, joint work with Samarth, Sinha. We all know that obtaining label is expensive and time-consuming. But active learning provides a solution for that and has a long-standing history. Approaches in active learning are 2 types: query synthesizing and pool-based methods. People have been using generative models to query samples in specific domains. Despite being successful, they have limited applications. In the pool-based active learning regime, a small portion of labeled data is available in the beginning. Then a model gets trained on that and is tested on the unlabeled samples. Different heuristics have been used to select samples based off of these predictions. One strategy is to explicitly measure the uncertainty and send the most uncertain samples to be labeled. The other strategy is in the case of having a committee of task learners, where the instance with the largest disagreement get to be selected and sent to the oracle. In the deep learning era, representation methods such as coreset or common uncertainty measurement tools such as ensembles or dropouts have been also tried for sampling strategies. But what is the common caveat in these methods? Well, these methods depend completely on the performance on the mainstream task, hence becoming a chicken and egg problem. Also in these methods, outliers have the same chance to be queried as mispredictions do. Here we introduce our approach called Variational Adversarial Active Learning, or VAL. We start with a large unlabeled and a small labeled data pools. In our approach, instead of relying on the task for querying samples, we learn a low-dimensional representation using both the labeled and unlabeled data encoded and decoded using a variational autoencoder. This makes our approach to be task agnostic. For our sampling strategy, we train a discriminator on the VAE's latent space that learns how to distinguish between encoded features and predicts which pool each sample is coming from. While the VAE tries to fool the discriminator to think that all the input data is coming from labeled pool, the discriminator attempts to effectively estimate the probability a sample coming from either of the pool. Once the VAE and discriminator are trained, we use the probabilities associated with the discriminator's predictions to select a certain number of samples and send them to the oracle. The intuition behind our sampling strategy is that the samples detected as unlabeled by the discriminator are the most probable samples to be different in the labeled data. Here we present our results on image classification and segmentation data sets. Here you see the image classification accuracy on ImageNet dataset plotted against percentage of labeled data. In order to have a fixed accuracy, let's say 52%, VAL requires 60,000 fewer labels compared to the best baseline. We also evaluated VAL on segmentation tasks on Cityscapes and Berkeley Deep Drive. VAL consistently outperforms and reduces the annotation effort by 5 to 10%. Considering the difficulties in full-frame instance segmentation, this translates into saving hours of time and effort for such dense annotations. To find the key roles in our model, we ablated the discriminator, the VAE, as well as the adversarial role of the VAE, and compared them all to random sampling. Eliminating the VAE and having only a discriminator as an image classifier in the image space yields the poorest results, even worse than random sampling. Whereas eliminating the discriminator and training a VAE that uses distances from the cluster centroids to explicitly measure the uncertainty yields the second best results after VAL, which implies the importance of uncertainty measurement in active learning. We also made sure of val's robustness in case of having a biased initial label pool where 10 or 20% of classes were missing, or when the labeler is prone to make mistakes on ambiguous pictures, and observe val consistently performing well in such cases. The sampling strategy of an active learner ideally has to be as fast as a random selection while performing better on the task. Although it remains challenging to beat random sampling time, val shows at least 50% improvement over the previous state of the art. In conclusion, we introduced val as a task-agnostic, pool-based algorithm that uses adversarial learning for querying samples. Val is time-efficient and scalable. Our code is publicly released, and we hope to see you at poster number 1. Thank you.
Good afternoon, everyone. I'm Xiaofeng. It's my pleasure to present our work, Confidence Regularized Self-Training. This is a joint work by CMU, NVIDIA, and GM. Unsupervised domain adaptation is an important transfer learning with wide applications. Due to domain gaps, model trained on source domain often suffer from significant performance drop when testing on different target domains. Considering this issue, unsupervised domain adaptation seeks to remediate domain gaps by leveraging unlabeled target images. So self-training is a powerful method. It tries to iteratively predict the pseudo-label on target and retrain with top confident one. Here we show an example on GTA 5 to Cityscape. An initial source model is trained with source-labeled images. Self-training involves the iterative process of pseudo-label generation and network retraining. The process is conducted upon convergence. Mathematically, the above self-training process can be formulated as a unified loss, which we will show in the next slide. So actually, in our ICCV19 paper, we propose a class-balanced self-training by treating the target domain pseudo-labels y-hat as latent variables. The pseudo-label can be either one hot or zero vector. A zero vector indicates ignoring the sample in the training. Lambda k could rebalance the confidence of each class to prevent the diminishing of small classes. The solution of pseudo-label depends on two things: the argmax of balance softmax and whether the confidence is above the threshold lambda. So since pseudo-label are one hot, self-training is essentially entropy minimization. An upcoming issue is making overconfident mistake on pseudo-labels. Such mistakes often come from two cases. The first is imperfect model, and the second is inherent label ambiguity. Since target domain labels are unknown, such mistakes can accumulate and get magnified towards trivial solution. In this work, we propose to address this issue by confidence regularization. There are different ways to achieve confidence regularizations. Well, the first is label regularized self-training, where we introduce a smoothness promoting regularizer on pseudo-labels. While with the regularizer, the generated pseudo-labels are soft, and thus promotes smooth network outputs in self-training. Here, alpha changes the sharpness of pseudo-labels. As alpha increases from 0 to infinity, its pseudo-label changes from one hot to uniform distribution. The second one is the model regularized self-training, where a confidence regularizer is directly defined on network outputs. Although the pseudo-labels are one hot, network retraining is influenced by the regularizer to encourage smoother outputs. Again, as alpha increases, the network is encouraged to be smoother. In this work, we introduced 4 regularizers. For label regularization, we introduce LREMT, which is a negative entropy of pseudo-label. Its pseudo-label is reweighted softmax with temperature. We also introduce 3 model regularizer. MRKLD is the KLD versions between output and uniform distribution. MREMT is the negative entropy of output, and L2 is L2 known of the output. In the bottom, we show how introducing regularizer changes the loss curves under a simplified binary class setting. In all cases without regularizer, the optimal solution leads to sharp pseudo-label or alternate network output, while regularization promotes smoother ones. Note that MRKLD shows a steeper gradient against the sharp outputs compared with the others. This is probably why it is performs best. We first test CRST Vista and Office for image classification. MRKLD and LREMT achieve the best single regularizer performance on both settings. The combined MRKLD and LREMT achieved even better performance. We also evaluated for segmentation on both Sinha to Cityscape and GTA 5 to Cityscape. MRKLD achieved the best accuracy. In here, we also show some segmentation results on GTA 5 to Cityscapes. CRST gives the best quality compared with CBST and source model. So in conclusion, first, compared with supervised learning, self-training is an underdetermined problem. Second, our work showed the importance of confidence regularization as inductive biases to help domain adaptation. In practice, MRKLD is the most recommended. In the future, we believe this work could potentially inspire many other meaningful regularization or similar problems, such as different kinds of structure regularization. We have publicly available our code, and to know more about our paper, please come to our poster too. Thank you.
Hi everyone, I'm Serim. I'll be presenting a loss function which modulates the loss scale based on the prediction difficulty. When we ask the network what's in this image, network thinks this sample is too easy or too difficult. But for some cases, network gets confused by visually similar objects and produces bimodal prediction. When we see these sample outputs, although the confidence score on the target class have relatively high value, these samples are incorrect since the inference step chooses the label which has the highest probability value. So the goal of our project is to give the network good learning signal by leveraging prediction difficulty. While cross-entropy penalizes the same loss values for these cases, our loss function takes a relative score gap into account and applies different loss values based on the divergence of output predictions, so that the network can make correct prediction even in the presence of confusing cases. There have been some researches which tried to give the network good learning signal either by sampling hard examples or by reweighing the loss scales based on the class distribution. However, these work require data statistics beforehand or sampling heuristics. Our approach is to let the network decide the prediction difficulty by itself. Let's take an example of a bottle's image. This is the standard cross-entropy. When the network makes this output distribution, our loss function uses the K's probability, which is the highest prediction value from the background classes, to modulate the ground truth probability, which is the bottle's loss function. If the bottle's prediction output was lower than the K's probability, it gets more penalized than the cross-entropy and gets less penalized if it was higher than the K's probability, since the prediction is correct. In this case, the bottle's output is 0.2, which is less than the K's probability. It gets more penalty. And finally, network can give correct prediction by using anchor loss. This is the equation for our loss function. It is composed of two parts, the cross-entropy and the modulator. This modulator uses anchor probability to define the prediction difficulty and rescale the standard cross-entropy accordingly. If we compare the graph with other loss functions, this is a standard cross-entropy which penalizes the target class distribution. Focal loss suppresses the cross-entropy. Anchor loss redistributes the loss values depending on the anchor probability, which is automatically chosen by the network. To compare how the loss changes based on the network prediction, this time, network produces trivial score on the background classes, so the loss is suppressed. And it gets less penalty compared to cross-entropy. When the network makes a wrong prediction with high confidence, then the loss scale becomes large, and it gets more penalty. We also apply anchor loss to a human pose estimation. Human pose has spatial dependency between adjacent pixel locations. So when we design the anchor probability, we take the maximum prediction score from the circled area centered on the ground truth location and apply anchor loss to the background. Let's see the results. This is the performance table in image classification on CFAR dataset. The sample outputs show that the network can successfully discriminate visually ambiguous images. This is a result in human pose estimation. We can get comparative performance with hourglass variants, which have higher computational complexity, by using only the baseline architecture plus anchor loss. We visualize the output heat map and the area where the anchor loss value is higher than the cross entropy. We can see that the network penalizes more on the symmetric parts or the parts from non-target person. Thank you for listening. If you want to discuss further, please visit our poster number 3.
Okay, so now let's bring all 3 speakers up on stage, and we'll give a moment for folks on the floor who would like to ask a question to approach a microphone. Okay, there's a question down here.
I have a question for anchor loss. You mentioned that when the network itself predicts the difficulty of prediction, and this can make it predict difficult cases better. And how doesn't this cause it to be overconfident in some predictions? I don't understand how it can be more confident when the task is more difficult and less confident when the task appears to the network to be easy. So are there any overconfidence issues with anchor loss?
I don't quite understand what overconfidence means, but this loss is designed to emphasize more on the hard examples.
Oh, I see. Thank you.
Other questions from the floor? Remember that you can ask questions online by going to slido, sli.do with hashtag ICCV2019_D1. Question for the first speaker. Can you say something about why you think the task agnostic models work better than the task dependent ones, or why you chose that?
Sure, because that's a very good question. Because relying on a model that hasn't been trained to train your active learning agent results in overfitting to the mispredictions made by the model just because it hasn't been trained well yet. So that's why we thought that the active learning agent should be trained without relying on anything about the task. Yeah.
Then another question for you. Can you say something about the robustness of the technique? Were the results that you obtained from a single fixed initialization or from multiple runs?
Sure. Yes, we did multiple runs, and we made sure that it is robust against the initial labeled pool, not to have same number of classes from all, number of images from all classes. So we intentionally removed some of the classes, so the model had to do zero-shot learning if it would have been trained. And also, we had a biased labeler by making mistakes on some examples, some of the classes. It wasn't meant to be an adversarial attack, it was just mislabeling.
Another question for the third speaker. So can anchor loss be applied to other tasks such as semantic segmentation or object detection?
I think we can also apply anchor loss to object detection, but for segmentation, so if you design the anchor probability to define the difficulty of the segmentation I think we can also apply anchor loss to those tasks.
Okay, great, thank you. So now we'll move on to the next group of speakers.
researchers have shown substantial interest in unsupervised learning, mainly due to the next several reasons. First, although large-scale label datasets are very useful, they are still expensive to correct. Label datasets such as ImageNet and kinetics requires a lot of money and people efforts. However, their sizes are still significantly smaller compared to the readily available unlabeled data, which cannot be used by unsupervised learning algorithms at all. Moreover, animals, especially humans and primates, are living examples for successful unsupervised learning algorithms, indicating how promising these algorithms are. In this work, we propose a new unsupervised learning algorithm called local aggregation, or LA. We illustrated this method in large-scale visual learning tasks and show that LA achieves state-of-the-art performance on multiple benchmarks regardless of the architectures used. Before introducing our method, I will first give a brief review on two previous state-of-the-art methods, deep cluster, or DC, and instance recognition, or IR. Both of them have the similarity that their objective functions are defined on the distribution of all the image embeddings. For DC, it applies k-means to group all the embeddings into smaller clusters. Then it further trains the network to predict the assigned cluster labels. These two steps are iterated to get the final network. As for IR, it optimizes the representations so that two views of the same image will be similar in the embedding space, and each image is far away from others. This is similar to memorizing and recalling one image. They both have problems. For DC, it needs a big last layer to predict the cluster label, and this layer also needs to reset every epoch due to the arbitrary cluster labels, making the training ineffective. As for IR, it separates very similar images, even though they should be aggregated. Realizing these problems and trying to adjust them, we then propose local aggregation method. In the embedding space, LA dynamically identifies two sets of neighbors for each example. After that, the current example as a red dot is then optimized to be closer to the close neighbors as the blue dots and also to be farther than the background neighbors as the black dots. Meanwhile, optimization aggregates two views of the same image, similar to IR. Taken together, our method is effectively a conceptual combination of DC and IR. Next, we evaluate LA and compare it to others. A scheduled pipeline is first training the networks, usually AlexNet, on ImageNet, fixing the learned weights, and then training a linear readout layer for ImageNet categorization task. We first show two even earlier tasks, relative position and colorization. Both IR and DC show better performance than these two tasks, indicating their strengths. LA achieves significantly better performance on this benchmark. LA also successfully leverages the deeper networks such as Resin 18 and Resin 50. Moreover, its performance improvement is even bigger for these architectures. Our unsupervised Resin 50 performance has actually surpassed that of the milestone AlexNet trained with all the labels, representing an important progress in unsupervised learning algorithms. Concurrent or later than our work, this achievement has also been reported in other papers. In addition to this benchmark, we also test how generalizable the learned features are by testing their transfer learning performance on places datasets. Again, our method outperforms others by large margins. This time, we are even better than the supervised network trained on ImageNet. Similarly, we also find LA achieves even better performance on much bigger improvement over other methods using deeper architectures. Taken together, these results suggest that LA is indeed achieving state-of-the-art results on large-scale visual learning. Due to a time limit, we did not show the other benchmark we had tested, where we also get good results. Our codes in both PyTorch and the TensorFlow frameworks have been released. For more technical details, please refer to the paper or come to my poster. In the future work, we plan to apply LA to other domains. We have already illustrated the effectiveness of our method in video on the unsupervised learning in this follow-up paper. Please check it if you are interested. Finally, I would like to thank my wonderful collaborators and my advisor, my colleagues in the lab, and my funding resources. And thank you all for your attention. Thanks.
Hello everyone, I'm Wang from Shenzhen University. My presenting paper is PR product substitute for inner product in neural networks. The gradient of inner product with respect to which vector W is the data vector X, and X can be orthogonally decomposed into the vector projection Px and the vector rejection Ix from W. The projection Px is parallel to W and will update the length, called the length gradient, while the rejection X is orthogonal to W and will change the direction, called the direction gradient. So a question arises, which is the key factor for optimization, length gradient or direction gradient? To answer this question, we conduct several control experiments. These results show that the direction gradient is far more critical than the length gradient, which might be unsurprising. However, the direction gradient varies with theta. That means when theta is large, the direction gradient is large, but when theta is small, the direction gradient is small. We argue this may hamper the update of W. So while direction gradient varies with theta, take an insight into the geometric definition of inner product. The inner product only involves the information of projection Px. When the length of Px changes very little, the length of X changes greatly. So to make the direction gradient independent of theta, we should combine the length of Px and the length of X in the formulation of inner product. Firstly, we should make a trace and a range of them with theta consistent. So after a series of transformation, we employ a length of X minus the length of X to represent the information of X. To make the combination compatible with the rest of neural networks, we should keep the fault path identical. To do this, we introduce two coefficients, the absolute value of sin theta and cosine theta in the third row. We just have the fixed during backward path. Independent third row, we get the fourth row. The original inner product is the fifth row. We replace the length of Px with the combination of Px and Ix, get the sixth row. Independent, we get the final formulation of PR product. So why we call it a PR product? The standard inner product only involves the information of Px, while PR product involves the Px and Ix. So we call this formulation the projection and the rejection product of PR product for brevity. We analyze the gradient of PR with respect to theta. It can be formulated as a unified form like the Ryou equation. Compared with the standard inner product, the PR product changes the gradient with respect to theta from a smoothing function to a hard one. One advantage of this is the gradient with respect to theta does not decrease as theta gets close to 0 or pi, providing continuous power for optimization. We also explicitly analyze the gradient of PR with respect to which vector W. The result can be visualized like this. The PR keeps the same direction gradient to a length of X. So, but it changes the length of direction gradient to a length of X. So it's independent of theta and increases the proportion of direction gradient. The PR product can be applied in the fully connected layer, convolutional layer, and LSTM layer. We denote this as PRFC, PRCN, and PRLSTM. To validate the effectiveness of PRCN, we conduct experiments on classification. The PR version can typically outperform the corresponding backbone models. To validate the effectiveness of PRFC and PRLSTM, we conduct experiments on image capture. The PR version achieved the performance improvement across all metrics. To better understand how the PR affects neural networks, we plot the minimum of absolute sin theta. We found that for most of the layers, the minimum of absolute theta in PR is larger than the one in standard inner product, which means the weight vector and the data vector are more orthogonal. We argue this is the reason for PR product to take effect. That's it. For more details, welcome to our poster. Thank you for your attention.
Hi, I'm Seong-Gyun. In this talk, I will introduce our new regularization method, cut mix. This work is done with global AI research team members. Okay, image classification is a fundamental task of computer vision. Given a model, we train the model using training images and each labels. To train a better classifier, a regional dropout strategy was proposed, which is called cutout method. This method deletes a random region of an image to make an occlusion-robust classifier. This method shows a good generalization ability, but they cannot utilize the full image region, which seems to be inefficient. Let me briefly introduce our new method, cut mix. As you can see, cut mix is a simple method which cut and paste two images and labels. The target label is decided by the ratio of the pixel of each image. In this way, the classifier learns what and where the objects are in the image. I will summarize the key advantages of cut mix by comparing to other methods. First, unlike cutout, cut mix uses all input pixels for training. Comparing with mix-up, which interpolates two images and labels, our method presents more realistic local image patches. And also, cut mix is simple and easy to implement. It only needs 20 lines of PyTorch code. So to see the generalization ability of our cut mix, we train RegNet 50 on ImageNet with cut mix. As you can see, cut mix shows a great improvement over baseline, and cut mix also outperformed the existing data augmentation and regularization methods. In short, cut mix makes RegNet 50 be as powerful as RegNet 152. To see the localization ability of cut mix, we perform weekly supervised object localization task on CUB and ImageNet. Cut mix cut and paste image patches, so it helps to focus on less discriminative parts. And the experimental results show that cut mix successfully improves the accuracy on localization task. Beyond the image classification task, cut mix pre-trained model can be utilized as a backbone network for other tasks, such as object detection or image captioning tasks. As you can see in this table, cut mix pre-trained model shows great improvement over baseline on several object detection and image captioning tasks. Especially 2 percentage point improvements on MS COCO will be obtained by the backbone changes from RegNet 50 to RegNet 101 in other way. In short, choosing cut mix pre-trained model brings great performance improvements in transfer learning tasks. Now, I will conclude this talk and give some messages. If you need a strong classifier, then apply cut mix regularizer to your classifier. It is simple and easy to implement. If you need a better pre-trained model, then just download our pre-trained model and use them. Our course and pre-trained models are available online at this URL. Thank you for your attention. Please visit our poster number 6 for more details. Thank you.
So, can the speaker please come for the questions? While people in the room can get ready using the microphone for question, maybe I can ask one from our system here.
Hello?
Oh, well, go ahead.
For the second speaker, what do you mean that changing the inner product, rolling the possible path while keeping it unchanged, rolling the forward path?
Okay, thank you. You mean how I ensure I change the backward path without changing the forward path, right?
Yeah.
Okay. The most critical in the final formulation of a PR product, there are two coefficients. These two coefficients are absolute sin theta and cosine theta are held fixed during backward path. That means they are detached from neural network by detaching, that's to say, when backward, we will them as a constant value, not a function of theta. That's to say, don't derive the gradient of the two coefficients with respect to theta. So I can change the gradient of any product without changing the forward path. Thank you.
Okay, thank you.
A question to the last paper about cut
mix, yeah.
Yeah. What if the first image has little object in the middle, and the second image also has little object and in the middle, and so the objects essentially swapped, and you mixed labels, but the resulted image in fact get wrong label?
It is really good question. Yeah, there's a fast over that case on our comics training, but we empirically confirm that comics can improve the deep network. I guess the reason by even if the cropped and pasting image doesn't have any objects, then even though in the case if we blend the label, then we think that it's a kind of label smoothing effect. So yeah, and this is very similar to the cutout methods effect. So yeah, is that for your answer? Yeah. Thank you.
Okay, maybe more questions?
Here's one question.
Sorry?
Hello, here.
Okay.
Yeah. Question for the first speaker. So you're training this using through unsupervised approach, and you learn this representation. How do you ensure that representation actually captures the essential features for downstream task? Because downstream tasks could focus on different aspects of the image.
I think we are running out of time, so I'll make it short. We have different benchmarks on different tasks to make sure that the render features are evaluated in different domains, such as places recognition, such as object detection, such as object recognition. So we have ensured that the render features is evaluated in different benchmarks to show that they are general.
Okay, thank you. Let's thank the speakers again.
Hello, everyone. I'm Tianfu Wu. Welcome to my talk. This work is collaborated with Dr. Xisong. We are motivated by explainable AI, so-called XAI. XAI entails computing the rationale that are explainable to end users. Nowadays, deep neural networks are powerful, but still largely considered as a black box. Post-hoc explanations are usually adopted, with remarkable recent progress obtained. But they may not be feasible to what the original model computes. We are interested in learning interpretable model from scratch. Consider object detection. Fast RSN are the most popular frameworks. In the spirit of XAI, can we compute meaningful configurations for detected objects on the fly? And since object configurations are unknown in training, we need to unfold latent structures. Latent structure learning is not new. For example, the classic deformable part-based model. One of our previous work tried to integrate and/or grammar in latent structure learning, which is further extended in this work. But with the integration improve model interpretability, we have another previous work showed that integration can improve both performance and interpretability. So how to represent and unfold the space of latent structures? We are motivated by the tangram, which can express a large number of object shapes with small number of primitives using compositional and reconfigurable rules. Consider a 3 by 3 grid. The space of latent structure is represented by an AND-OR graph. There are 3 types of nodes. AND nodes represent binary decompositions, OR nodes represent alternative decompositions, and the terminal nodes ground symbols to data. Then how to integrate DNs and AOGs. We first compute terminal node sensitive feature maps. Then we compute terminal node values. Terminal node feature maps are then recalibrated by the learned values. Then object configuration are learned on the fly using dynamic programming in 2 phases. In the bottom-up phase, following the depth-first search order, we compute values for AND nodes and OR nodes using the sum and the max operations respectively. In the top-down phase, the path tree for each Li is retrieved following the breadth-first search order. Based on the inferred configuration, we compute configuration-aware features for the head classifier. So there are some details worth mentioning. 3 methods of leveraging terminal node values are tested. First, the baseline method uses the compute value as it is. Second, the sparsity-inducing method keeps the top k terminal nodes only. Third, the adversarial attack method suppresses the top k once. A bit counterintuitively, the adversarial attack method usually learns better configurations, but it is explainable since we use simple max operation for all nodes. To further address this issue, we utilize a folding-unfolding training protocol. At the beginning of training, we fold the AND-OR graph into an AND graph, such that all possible configurations get trained fairly. Then the unfolding protocol is followed for learning instance-specific configurations. Now let's see some experimental results. We call the flavor of XAI, and here is what our model learned, with the configuration superposed on an image and the path tree to the right. So a few more examples of cat detection. We observed comparable quantitative performance. We followed all the hyperparameters of the baseline model. So the slight performance drop could be animated if we tune those parameters accordingly. We also compared configurations learned by AOGs of different size. Here is the overall model learned in the Pascal VOC. We plot the histogram for each node. Potentially, this will be useful for learning to learn the synergy between different categories. Thank you. Welcome to our poster for more discussions.
Hi, I'm Jason. I'll be presenting our work on scaling object detection by transferring classification weights. In the domain of visual recognition, the number of object classes covered by image classification datasets are often in magnitude of orders larger than those of object detection datasets. Comparing the 2 images on the top right corner, we can see that it is significantly more tedious to annotate box-level objects than image-level objects. We focus on scaling the number of object classes handled by object detectors with the help of large-scale image classification. Our method is generally applicable to any existing object detection framework. Here we are using FasterRCNN. To start off, we have an image classification network pre-trained on a very large-scale image classification dataset. Part of the classes are shared with the object detection dataset, and a large number of them are novel classes not found in the detection dataset, which are colored in green. During training of the detector, we train a weight transfer network denoted by capital T that transforms the shared class weights from image classification network for use in the object detector to minimize object detection loss. During testing, we can apply the weight transfer network to transform the weights of novel classes as well. Conventionally, weight transfer network, or WTN, is a two-layer, multi-layer perceptron with FC layers. Here is an alternative view of the pipeline of transferring weights from classification network to detection network. Between the classification network CLN and detection network DEN, we have a vanilla WTN. We employ binary cross-entropy loss for multi-label classification on the training classes Chet and other found in the detection dataset. In the detection dataset, the shared classes provide training signals to both the WTN detection network, and other detection classes not handled by the classification network provide training signals only to the detection network. Although vanilla WTN works, it suffers from great underfitting due to anomalized input weights and class agnostic nature of the WTN network. We tackle the underfitting of with normalizations at input and feature levels per channel input standardization and group normalization GN. The resulting architecture on the right is called WTN+. We tried batch normalization, but it gives very unusual outputs and didn't work really well. On the left is the improved weight transfer pipeline with WTN+. During training, WTN is not aware of the novel classes, nor that the novel classes contribute to the training. Here we introduced autoencoder WTN+, AE WTN+, a novel WTN variant with encoder-decoder architecture. It reconstructs the input weights from the encoder outputs with a reconstruction loss. This helps preserve information of the novel classes and provides WTN and the detection network a comprehensive knowledge of semantic relationships between all the classes. We perform ablation study on the WTN Plus architecture with 3 evaluation sets from open images and visual genome, 1 for scene classes, 2 for novel classes. WTN Plus consistently improved the performance over vanilla WTN by at least 4 points. We compare our proposed WTN methods with various related methods that carry out supervised learning and partially supervised learning. We evaluated conventional regularization methods applied to WTN Plus to verify if conventional regularization can reach the performance of AEWTN Plus, which can be seen as a regularized model. As we can see here, the AEWTN Plus is the best performer among all. We compute the number of overlap neighbors of the transform weights and the original weights for varying number of nearest neighbors. As shown, AEWTN Plus can better preserve the local neighborhood relationships of the classes. Here are qualitative examples showing the novel classes detected by our method. They are in red boxes. Thank you. Please visit our poster for more details.
Good afternoon, everyone. I'm Yun Taochen from Institute of Automation, Chinese Academy of Sciences. In the next 5 minutes, I will give a brief walkthrough of our scale-aware Trident networks for object detection. Image-based recognition tasks has always faced the challenge of scale variation of objects. The projective nature of 2D images makes faraway objects look smaller than the closed ones, even if they are of the same size in the 3D reality. For instance, the feet of the bird are a very distinct feature, but the convolution gets a very high response for the feet of a large bird will certainly miss the small ones. This example demonstrates the scale variation problem for existing object detection. Ideally, we can normalize every object to a uniform scale like we did for the image classification task. But the scale of all objects in an image changes altogether, so we have to construct a multi-scale pyramid for scale normalization. The most widely adopted pyramid scheme is an image pyramid. The image pyramid utilizes a single network and multiple images of different sizes. Each image goes through the same network, and the detection results are combined with NMS. The image pyramid is simple and effective, but the most prominent problem of it is the increased computation. This is especially true when we are processing small objects on a large image. Another line of work tries to construct a multi-scale pyramid from feature maps of a single image. The feature pyramid saves computations over the image pyramid by reusing features of different sizes generated from a same network. But reusing features will introduce semantic discrepancy between small and large objects. As shown in the diagram, features of different pyramid levels are generated by different set of parameters. This reduces the effective number of training samples for each scale. Another line of work tries to, in order to obtain an efficient and uniform feature representation for object detection, we propose a novel structure called the Trident Network. Trident Network has a multi-branch structure where the convolutions in each branch has different dilation rates, but share the same weights. Here, the different dilation rates for each branch help us to normalize the scales efficiently, and weight sharing between branches ensures a uniform feature representation. Our detector takes a single image as input and firstly transforms it with a shared backbone. We then stack multiple Trident blocks on top of the shared backbone to generate scale-specific feature maps. During the training, only the objects of proper scales for each branch are selected for training. Final results are aggregated with NMS. Here we show how to construct a Trident network from a residue network. This could be done by simply swapping the top residue blocks with our Trident blocks. And all branches of Trident network share the same RPN and RCN subnetworks. Here come the ablations. We can see from the table that the multi-branch structure alone contributes to 1.1 in MAP. Weight sharing contributes another 1.3. And the scale-aware training scheme mainly contributes to the performance of small objects. Although our Trident network is efficient compared with the image pyramid scheme, but the multi-branch structure will still add some extra flops compared with the feature pyramid. Here we proposed a single branch approximation of our Trident network, which is dubbed as Trident Net Fast. During the training, Trident Net Fast utilizes 3 branches without the scale-aware scheme, and only the middle branch is kept during the test. Since we adopt the weight sharing training, Trident Net Fast is essentially equivalent to the within network scale augmentation. As shown in the right table, Trident Net Fast attains most performance gains of the original Trident network while being as fast as the vanilla faster RCN detector. Here are some take-home messages. First, multi-branch network is an effective new way for scale normalization. Second, weight sharing across branches help us to fully utilize the training data. Finally, multi-branch training and single-branch testing is both fast and performant. Thanks for your audience, and welcome to our poster for further discussion at number 9. Thank you.
Okay, let's bring the speakers back on stage, and folks who have questions, please approach a microphone. And in the meantime, I can ask a question. I'll ask a question of the first paper. So for the first paper, So I'm wondering is there some way of quantifying explainability, or can you somehow measure how explainable your model is?
Yes, that's a good question. So right now we focus on extractive rationale, which is qualitative. So yeah, in order to capture the quantitative explainability, we can evaluate the detection on with some part segmentation. So then we can evaluate each learned part to see how semantic meaningful it is. So it's our ongoing work. Thank you.
And then another related question for you. Does your model outperform baseline models that aren't explainable? And if not, could it give some insight in how to do that?
Right now we observed slight performance drop. I think mainly because we didn't tune any hyperparameter. We adopt all the baseline hyperparameter. But our model introduces a pretty complex angle graph, which may need more training. So we are fine-tuning that.
Any questions from the floor? Okay. For the third talk, sorry, there's a question about whether the Trident slows down convolutions. You can come up to the microphone, please.
As indicated in our slides, the Trident network has a fast version called the Trident Fast, which will consume the same flops as the original detector, so it will not slow down the process speed while maintain almost all the performance gains.
And we have a question about whether this could be used for other kinds of invariants as well, like rotation or other things like that.
Yes, we have some initial thought about applying it for video object detection or other things, kind of video action recognition or this kind of things.
Maybe one last question that is asked online for this paper. Could you comment how it relates to the FPN?
Actually, in our paper, we made a comparison with FPN. Our method outperformed FPN by a margin. You can come to our poster and further discuss this.
For the second paper, do you have some intuition for why your architectural changes are the right things to do?
So we propose two kinds of architecture. One to counter the underfitting of the WFTN architecture. So that helps it fit the data better and achieve better performance. For the second architecture, we use reconstruction loss to achieve like auto-encoding to the architecture and allows it to like retain more information about the classes so that it could perform better for those unseen classes.
Okay, thank you. Let's thank all the speakers again.
Hello everyone, I'm Satoshi Kosugi from the University of Tokyo, Japan. Today, I'm going to present our work, Object-Aware Instance Labeling for Weakly Supervised Object Detection. Our research topic is Weakly Supervised Object Detection. Unlike supervised object detection, we cannot use bounding box information and only know what objects are contained in each maze. One of the previous methods is online instance classifier refinement. In this study, multiple detectors are trained using the previous detector as supervision. Through the iterative update, detectors and bounding boxes are refined gradually. In order to obtain efficient iterative update, we focus on the way of supervision, which we name instance labeling problem. Instance labeling is a problem of which label should be annotated to each region based on the last localization result. These labels are used as the supervision for the next detector, so the performance of the next detector depends on the labeling method. In the previous method, OICR, they employ a rather simple labeling method. The top scoring and highly overlapping regions are labeled as positive. And the all other regions are labeled as negative. However, this labeling method has two problems. First, regions covering only a part of the object are labeled as positive. Second, the other objects are labeled as negative. These problems reduce the performance of the net detector. To solve these problems, we propose two labeling methods. The first one is context-aware positive labeling. This labeling method is intended to find regions covering the whole object. For this purpose, we focus on Tanaka et al.'s work. They worked on classification with noisy labeled images, such as a dog image labeled as a cat. They argue the training loss differs depending on whether the data is noisy or clean. As shown in this graph, the loss decreases for clean images and is hard to decrease for noisy labeled images. We use this characteristic to judge whether a region covers the entire object. We take a dog image for an example. We first fill the inside of each region and then label these images as a dog and train a classifier. If a region covers only part of the dog, the filled image is clean because the dog is visible outside the region. Whereas, if a region covers the entire dog, the filled image is noisy because the dog is not shown outside the region. By using the difference in training losses, we can select only regions covering the whole object. This is the first labeling method. The second one is spatially restricted negative labeling. In OICR, the top scoring region and regions whose IOU is higher than 0.5 are labeled as positive, and all other regions are labeled as negative. As a result, other objects are labeled as negative. To avoid this problem, we impose a spatial restriction on negative labeling. That is, we ignore regions whose IOU is lower than 0.1. Only when IOU is between 0.1 and 0.5, the regions are labeled as negative. These two labeling methods are our proposed methods. We evaluated the proposed methods on Pascal VOC 2007. This result shows our two labeling methods achieve higher performance than OICR, and its combination outperforms previous state-of-the-art methods. These are examples of the detection results. Our method can effectively reduce false positive compared with OICR. That's all. Please check out our poster at number 10. Thank you.
Hi, good afternoon. I'd like to present my paper, Generative Modeling for Small Data Object Detection. And this work, we know that GAN can do lots of cool works, including transferring a painting to a real-world images or some sketch to back images. Those are all cool. But on the other hand, we want to use GAN for generating synthetic images for small data object detection. More specifically, we may have some tasks that actually have very limited amount of labeled data, maybe because those data are very expensive to annotate or is actually naturally rare. In this case, we may also have some background images that are easy to collect. So what we want to do is we synthesize labeled positive data by inserting objects into the background images. And then we have more data to train the object detector. Some examples are medical disease detection. And here, we want to say, can we just use existing GANs to generate synthesized data? Well, the answer is probably no, because I have this paper.
And the reason is we have this discriminator and the generator loop where they affect each other during the training. But at the end, we take the generated image and fit it into detector. But the thing is, we never know whether the generated image can help detector or not, because detector never gives any feedback to the generator to say, oh, this image could help me, that image cannot help me. So in this case, we would like to bridge this gap from the detector back to the generator by integrating a detector into the GAN loop. And then it can provide direct feedback to the generator to improve the performance. So overall, it's like we use detector GAN to generate some synthesized data by inserting objects, and then combine it with the real data to train a detector to see whether the detection is improved or not. So the main issue here is we care about the loss or the detection loss on the real image, but actually in this loss pipeline, we don't see the generator here. It's only about the real image and the detector. But fortunately, we also know that the detector is actually trained with both synthetic image and real image. And the synthetic image is actually generated by the generator. So if we unroll one training step of the detector, we will see that the generator can be linked further to the detection loss on the real image. So by using this, we can have a way to train the generator with detection loss. Here are some results. First, we would like to show that this method actually can help to improve object detection. So we compare using real data and synthetic data from the detector GAN with using only real data or using some other synthetic data from traditional GAN works. And we show that we improve both on the average precision and also the recall. So we dig into it to see what exactly are the synthetic data are helping. So what we see is, first, we actually can help the detector to capture more modules. Like in the right figure is the detector GAN result. We can capture more modules than just using the real data. And also we can see the bounding box locations are actually more accurate while we're using more synthetic data here. And next, we want to show that the generated images are actually quite real. So these two are two examples of nodules inserted into X-ray images. But of course, I'm not expert to see whether X-ray image is real or not. So we ask radiologists to label, whether we are better than some other baseline or not. And turns out they prefer our work much better than cyclogram baseline. And the next part is we want to show that the detector GAN concept by integrating a detector into the GAN loop is actually can be applied to many other works or domains. So this one is a pedestrian detection domain, and what we use is a different backbone than cyclogram. It is peaks-to-peaks and some other work based on peaks-to-peaks. And what we do is we integrate the detector into the loop and see improvement. Here are some examples of the generated image. And to summarize, we have integrated detector into the GAN loop to have better performance, more real image, and we are applicable to other GAN structures as well. Yeah. Thank you.
Hello, everyone. Here I present our work on transductive zero-shot detection. This is a joint work in collaboration with Australian National University, Data61 CSIRO, and Inception Institute of Artificial Intelligence. Zero-shot learning attempts to recognize objects which are not observed or seen during training. In contrast, zero-shot object detection tries to detect both object labels and associated bounding boxes, which are not available during training. The detection version is relatively unexplored research problem as compared to the zero-shot recognition task. Similar to the recognition version, zero-shot detection methods also suffer from domain shift, which is a data distribution mismatch of seen and unseen data domains, and the biasness problem, which is learned model predicts higher score to seen than unseen classes.
In this paper, we propose a transductive zero-shot detection approach that convincingly reduces the mentioned problems. Being a transductive solution, we have used test data as an unlabeled set during training. Now I describe the specific problem what I have addressed in this paper. During training, we have training images with scene instances, ground truth scene labels and bounding boxes, word vectors of object classes, test images without any ground truth annotations, and our task is zero-shot detection to predict ground truth unseen labels and bounding boxes, and generalized zero-shot detection to predict ground truth seen and unseen labels and bounding boxes. Transductive learning for zero-shot recognition and detection has some major differences. For recognition, if an image is coming from unlabeled test data, the model knows the image is from unseen because there is only one prominent object per image. In this way, the information about which image has seen and which image has unseen are known during training. But for detection tasks, an unlabeled test image may contain both seen and unseen objects together, and there is no annotation to distinguish between seen and unseen objects and their locations. Another issue is transductive zero-shot recognition usually follows pre-trained feature-based learning. It helps to create a batch with both labeled and unlabeled data, but for detection tasks, we want to perform end-to-end learning, and one image can have thousands of anchored boxes, so we cannot use many images in a batch. Therefore, transductive learning for detection is more difficult than recognition. This is our overall approach. It has an inductive model and a transductive model. We first train our inductive model using a previously published approach that does not use any unlabeled data. Then, taking advantage of the inductive model, we train our transductive model. At first, unlabeled data is fed to the inductive model to generate fixed pseudo-labels. Then, transductive model is initialized with an inductive model. After that, unlabeled data is fed to the transductive model to generate dynamic labels. And fixed and dynamic labels are then fed to the transductive model to iteratively update it based on a hybrid loss calculated from fixed and dynamic pseudo-labels. The initial decision boundary of an inductive model, solid black lines here, is updated to a modified decision boundary, blue dashed line, after the transductive learning. Here we illustrate the overall network architecture and the loss. The architecture is similar to RetinaNet. The only change is that the reddish layer at the subnet branches contains semantic word vectors as fixed weight. At the final layer of the classification branch, we have fixed and dynamic pseudo-level based loss. For the fixed part, the loss is basically a focal loss based on seen and unseen pseudo-levels from the inductive model. The dynamic pseudo-level loss has three components. First one works on seen prediction. The second one works on unseen prediction. Both are a version of focal loss again that utilize dynamic pseudo-levels. The third part tries to maximize unseen predictions because unseen scores are usually lower than seen scores. It makes a balance between seen and unseen scores. Also, it helps to improve generalized zero-shot detection performance. The overall loss is the weighted sum of the fixed and dynamic pseudo-labels. Here are some quantitative results on MS-COCO and Pascal VOC dataset. We evaluate the performance based on mean average precision and recall. We compare our work with several recently published inductive methods and the transductive baselines while performing zero-shot detection and generalized zero-shot detection. Our task successfully outperforms other methods. Here are some qualitative results. The red bounding boxes are representing unseen and green bounding boxes are representing seen classes. The top two rows are showing zero-shot detection and the bottom two rows are showing generalized zero-shot detection results. In conclusion, we propose an end-to-end trainable solution for transductive zero-shot detection and generalized zero-shot detection by employing fixed and dynamic pseudo-level based loss. In experiment, we have achieved state-of-the-art performance on MS-COCO and Pascal VOC datasets on this problem. For more detail, please come by at our poster number 12. Thank you.
Thank you. Can all three speakers come to the stage for questions? Are there questions in the room? Yeah, Alyosha?
I have a question for the second speaker. It's a very nice work, but I'm very worried about the use of medical data as an example. Mm-hmm. You're basically synthesizing fake medical records, and one issue here would be that you're going to be very biased to the very small true image data set. Yeah. And you're basically giving the doctors a free pass instead of going there and getting more data, they feel good about, getting all this fake data, but are you really overfitting to that small image, real subset?
Yeah, thank you for the question. So as I kind of mentioned, if you only really have small amount of data, then you're just fitting that. But what we actually have is lots of background image that are actually, during the training process for the detector, we're not using the background image that. So we're using those things and try to insert the objects, try to create new combination of foreground and background. And I think this can bring some more information to the training. But another question is, of course, whether it's kind of limiting the doctor or preventing them to actually collect more data. I think it's too lying, because doctor, of course, can create more data by annotating more. But when they annotate more, we can also generate more. So we can also improve upon what they have collected. But on the other hand, this kind of task is really hard because the nodules are just naturally rare. It's not like they won't annotate more. Yeah.
But you're not changing the nodules, right? You're just flipping the background. The nodules are whatever they are in the training data. That's the only thing you have, right?
Yeah, so we're not directly copy pasting, but it's generating, but still the nodule are still just in the original data, but with some interpolation possibly. Yeah. Thank you.
Are there more questions from the audience? No? Then maybe I have a question for the first speaker. So you propose two ways to improve the weakly supervised object localization, and the second one is this sampling of the negative, where you restrict to a certain set to avoid having false positive in your set. Can you comment on the if it restricts the diversity of the examples, and if you observe that, and if it has an impact? The fact that you restrict the set of negative when you retrain your detector, do you have less diverse examples, negative examples for training in your method? And does it have an impact?
You mean the number of images which contains multiple objects?
Yes.
About 20% of all images contain multiple objects. So.
Okay. And on those images, can you comment on the diversity of the negative set you sample?
Diversity.
Well, don't worry, you can take the discussion offline. Yeah, okay, I think it's time to stop. Thank you. Let's thank the three speakers again.
And before the next talk, there's reports on Slido that the room is a little bit noisy, so particularly if you're in the poster area, if you could please keep your voice down while you're chatting so that it doesn't interfere with what we're doing here. And then on to the next talk.
Hello everyone, I'm Seong-Gyun Kim from KAIST, South Korea. I'm going to present our paper, which is about domain-adaptive one-stage object detection. Domain adaptation transfers knowledge from the label-sufficient domain to the label-scarce domain. For several years, domain adaptation has been researched variously. However, most of them are developed for classification. Also, there are some works for semantic segmentation recently. For object detection, there are only small number of researches. In this paper, we solved the problem of domain-adaptive object detection. We used SSD for our base network, which is one-stage object detector. To the best of our knowledge, previous works are based on faster RCNN, and they proposed some instance-level alignment techniques. However, those techniques cannot be used to one-stage object detectors. This property of one-stage object detectors makes it hard to apply instance-level alignment techniques. We want to point out several problems that occur when we apply domain adaptation to object detection. First, features extracted from object detectors have high complexity because detection task is both multi-label and multi-instance problem. We also figured out that background examples share less common features, and thus global feature alignment approach is not effective. Second, there are two types of error in object detection, false positive and false negative. These both errors make self-training approaches ineffective for object detection tasks. In this paper, we claimed that simple global feature alignment enforces to align non-transferable backgrounds. Instead of that, we proposed background score regularization, which enhances the network's capability to discriminate between foreground and background. We trained the network in an adversarial way to do this. The adversarial loss is the binary cross entropy loss, which has a value of t for a ground truth value. Here, t is set as 0.5. We separate SSD into a feature extractor and a classifier. For target inputs, we regularize the classifier to predict with less certainty. On the other hand, the feature extractor is trained to maximize the adversarial loss to deceive the classifier. By this adversarial training, the feature extractor will learn discriminative features. However, the adversarial learning is unstable due to a large number of detections. We randomly selected foreground and background examples for learning. Furthermore, we added the focal term in the adversarial loss to stabilize the training process. Our second proposed method is weak self-training. For object detection, image level labels play an important role to reduce errors in pseudo-label. Many previous works utilize image level labels, but we are under unsupervised setting and cannot access to any types of labels. We proposed SRRS to reduce false positive error. Before non-maximum suppression, we utilized all detection results around the final result. This SRRS score is used when we choose the positive examples. Negative examples chosen from hard negative mining have a large potential of being foregrounds. In a self-training situation, hard negative mining refers to incorrect pseudo-foregrounds and selects background examples with the highest confidence loss values. Thus, we chose a portion of negative examples that have the lowest confidence loss value among the results of hard negative mining. We experimentally show that our approaches make improvements under unsupervised domain notation situation. We used Pascal VOC dataset as a source domain and Artmedia dataset as a target domain. In this paper, we tackled unsupervised domain notation for one-stage object detection. We reduced the domain shift by enhancing discrimination between foregrounds and backgrounds of the target data. And also, we diminished adverse effects of pseudo-labeling. Thanks for your attention. See you at our poster number 13.
Hello, this weekend it's my grand honor to present our work, Memory-Based Neighborhood Embedding for Wave Recognition. The co-authors are Dapen Chen, Bin Liu, Nenhai Yu, and Ryou. Learning good feature banding is vital for image recognition. With the ideal feature bandings, classification tasks could be reduced to a nearest neighbor problem, and the ritual task could be easy by examining image relationships. Current methods focus on design network architectures, not functions, but ignores neighborhood information. Consider the following case. The feature embedding of two different clusters can be very close to each other. However, if taking the feature embedding and its neighborhood into account, two close feature embedding can be classified into different clusters, and the affinities to the neighbors can be interused to modify original feature embeddings. To incorporate the neighborhood information, we need to solve two problems. That is, how to acquire more relevant neighbors for the network training, and how to aggregate the neighborhood information for more discriminated embedding. For the first problem, we augment our memory module into the network. And for the second one, we organize the target neighbors as a tree graph. In summary, we propose a neighborhood embedding framework. It can be separated to memory module and the neighborhood embedding with tree graph. Next, we will introduce each module. For memory module, it involves memory construction and memory update. For memory construction, we initialize the memory with the features and associated labels from pre-trained backbone network, and we update the features corresponding to current training examples in memory by newly computed features from same backbone in training stage. With the memory, then we can retrieve neighbors for each target instance. For exploring the neighborhood information, the neighbors are organized in a tree graph with the target instance as the root node. Each time, we extend all the leaf nodes by adding the candidates neighbors from the memory as the new leaf nodes. The tree graph grows until it achieves a predefined depth. And the nodes in the tree graph do not have boundary information. Thus, a standard neural networks like scenes cannot be directly applied. To handle the graph input, we iteratively perform variation on more connected nodes, which gradually propagates information within the graph to the target instance. Each time, we update the features of all the branch nodes in the tree that drops the leaf nodes. Finally, the tree remains only one node, and its embedding is fine neighborhood embedding of target node. In general, our proposed attention aggregation can be defined as follows. The formal appreciated procedure of taking weighted average of neighboring features, combined with previous feature, then going through a linear activation. For feature embedding, we hope neighbors belonging to the same class with target node have more contributions than ones belonging to other classes. So the attention weight is designed to be proportional to the probability of two nodes belonging to the same class. We conduct experiments on two tasks, image search and filter learning. For our birth study, we study about memory update strategy and memory size, and study the effect of number of neighbors and tree graph depth. And finally, we compare to our method with previous methods, and our method achieved state-of-the-art performance. For more detailed information, please come to our poster. Thank you.
Hi everyone, I'm Zhou from UIUC, supervised by Professor Thomas Huang. Our paper is self-similarity grouping, a simple unsupervised cross-domain adaptation approach for person identification. Person ready is a task of recognizing a person body captured by different cameras over multiple candidate targets. Because of its essential applications in security and surveillance, person ready has been drawing lots of attention from both academia and industry. Recently, person ready has achieved pretty good performance on multiple benchmark datasets using deep learning methods. But deep ready models trained on one single dataset may have a significant performance drop when directly tested on the target dataset. This drop can be as large as 67%, from 80 to 26 in MAP. That's because there's always large domain difference among different datasets. Manually annotating all the images in the target dataset is infeasible and time-consuming.
Thus, the high-performance supervised model cannot be well deployed to real-world applications. So our goal in this paper is trying to achieve a comparable performance with no or just a few annotations. In another word, we work on adapting the pre-trained reality model to another dataset with unsupervised or semi-supervised learning. Here we proposed a method called self-similarity grouping, in short SSG, to achieve our goal. Without any true labels in the target dataset, we want to mine the similarities among all person images. Different from previous works, we find those similarities from global to local manner. That is, we use the visual cues not only from the whole body, but also from the upper parts and the lower parts of the body. As shown in the figure, we first split the image into whole body, upper part, and bottom parts to extract the features using a pre-trained model, and then applied unsupervised clustering method to assign pseudo-labels to them, and finally fine-tune the model on the new data sets. So here is the detailed pipeline of FSG. So given a target with unlabeled samples, we first extract the features using a ResNet 50 pre-trained on the source dataset, and split the extracted features into whole body, upper body, and bottom parts. We then try to use global average pooling to process those features and conduct its unsupervised clustering method to assign pseudo-labels for each cluster. Note that the labels for different body parts can be different. Finally, we fine-tune the model using the assigned new labels. We further extend the unsupervised reality SSG to a clustering-guided semi-supervised setting. We call it SSG+. It is feasible since in practical, we can manually label some of the samples in the target dataset. In SSG+, we randomly selected a single image in each cluster to assign the true labels. Other labels are assigned not by the clusters, but by the k-reciprocal distances between the labeled and unlabeled samples. Nearest samples will be assigned the same labels. So we conducted step-based learning to progressively explore the whole dataset. The above-mentioned SSG and SSG+ share the same feature space, so we propose to jointly train them in a new framework. We call it SSG++. Specifically, we apply the combined loss and use step-based learning until it is stable. So here shows the performance we achieved using the above three models. As we can see, there are a big performance drop when we evaluate the pre-trained model on a new dataset. The proposed unsupervised methods, SSG, and its developed version, SSG++, can recover the performance back to a comparable level. So when comparing with all the state-of-the-art unsupervised methods, the proposed SSG still performs the best and improves the state-of-the-art by a large margin, say 1.6%. When transferring from Duke to market, our methods achieved 58.3 of MAP in unsupervised learning and 68.7 when we have few labels. When transferring from market to Duke, we also outperformed the state-of-the-art by 1.4%. In addition, we further evaluate the proposed SSG on MSIMT17 dataset, which is the largest and most challenging reality dataset. We improved the state-of-the-art by a large margin. It further verifies that the effectiveness of our proposed model. Our poster ID is 15, and the code is available online, so welcome to our posters and to discuss more details. Thank you.
Okay, let's bring speakers on stage, and folks who have questions, please head to a microphone.
Hello.
Yeah.
I have a question to the second speaker. So if we use your method in a large data set, so you have to store more features and search the neighbors in a much larger space. So will this influence the speed or the performance of your method?
Yeah. Okay, it's a good question. For large memory, if you use a large bench, large training data, you will get a large memory. So I think there are maybe two ways to design, solve it. First, maybe you can sample a subset of features of the original memory. And the second, you can torture the efficient, fast nearest neighbor search tools or algorithm to help you to search neighbors. Thank you.
Okay, thank you.
Okay, I'll ask a question from online then to the first speaker. One question is, have you considered applying your method to two-stage detectors like faster RCNN?
Oh, yes, actually I did it, and it doesn't work well. And actually I can say why, what is the reason. In the future I analyze more for that. Yes.
And then another question for you from online. Could you explain a bit more about how focal loss affects adversarial training?
Self-training?
The question is, could you explain a bit more, could you say a bit more about how focal loss affects adversarial training?
Focal loss that I added on the adversarial loss. So,
right.
We added focal loss to stabilize the adversarial training process. So in our paper analysis section, if we don't add focal loss term, the training process cannot converge and the loss values explodes. Yes, for more details, please come to our poster section.
Okay, and maybe a question for the third speaker. So to what extent could your techniques be generalized to problems other than person re-identification?
I think because this problem is pretty special because we cannot manually annotate millions of images. So actually, if we have few data like face recognition or other kinds of like vehicle ratification or other kind of ratification problem, which has the similar problems, like we do not have a lot of annotations, I think these methods can be greatly and well deployed to them.
Great, okay, thank you. Let's thank all of our speakers.
So maybe can the fourth speaker of this large batch of paper come on the chairs?
Hello, I'm Zima Liu, and I'm glad to introduce our work, the Deep Reinforcement Active Learning for Human-in-the-Loop Person Re-identification. So an unsolved challenge for the person-ready task is the expensive annotation cost with a gallery size far beyond queries. So how to cut down these expenses has practical significance for real applications. So that's why we intend to replace the traditional train once and deploy strategy with the human-in-the-loop training style. As you know, the human-in-the-loop can explore the human feedback in an incremental learning cycle of the machine. It especially works for the rapid model adaptation problems. So for the proposed approach, we employ a similar structure that requires the user to annotate only a few informative pedestrian paths recommended by an adaptive sample selection strategy. So this strategy is implemented by an agent network, and this network aims to sample the informative paths only. So the design of the action is to select one gallery sample at each time step. So the design of the state function should reflect the sample correlations among the input query anchor and the gallery pool. And also, like the other standard active learning approaches, we use the data uncertainty as the reward function. Here we use the triplet loss function. So the methodology of the proposed approach is as shown. As its query and the corresponding gallery pool comes, we use a deep network COMAC to extract the features. And those features can be used to compute a sparse similarity map, which is taken as the initial value of the state function. And later, this state is fed into an agent network consisted by 3 connected layers, and then output an optimal pair to the human annotator. So to save more budget, we only require the annotator to provide a binary positive or negative feedback. So in one way, this feedback contributes to the revision of the state function. The central idea is to strengthening the correlations of the positive samples and weakening the ones of unsimilar ones. And in another way, this feedback can use to compute the reward value at the current action. So this process will stop based on a predefined maximal annotation number, and with enough pairwise data to be collected, we can just fine-tune the parameter omega by a triplet loss function. So we conduct experiments on 3 re-identification data sets, including 2 large-scale data sets and 1 small data set. So for the market 1501 data set, we annotate over 8 million pairs for the fully supervised one. Well, for our approach, we only annotate around 10,000 pairs, which saves a lot budget, but still achieves quite good performance. So as you can see, only around 3 performance drop at rank 1 accuracies. So on the Duke dataset, which is also a large-scale dataset, only annotates around 0.12% pairs, but achieves favorable performance. This also validates that our approach is good for the large-scale datasets. So this CUHK01 is a small-scale dataset, and we annotate around 1% pairs, and also achieves quite good performance, around 5% performance drop at rank 1. So in conclusion, the proposed approach learned a joint framework of active learning and reinforcement learning. And also we train an adaptive annotation strategy which works for the specific human-in-the-loop person re-identification. And what's more, this approach achieves a more realistic and rapid ready domain adaptation deployment, which works for the large-scale surveillance systems. So thank you for your listening. If you have further questions, please come to our poster number 16. Thank you.
Hello everyone, this is Junchen Chen, and I'm going to present our work for vehicle re-identification. First, I would like to acknowledge the support of our sponsor. The objective of vehicle re-identification is to retrieve all images of a vehicle of interest in a large image gallery of vehicle captured in a set of different traffic cameras in different conditions, including different location, viewpoint, and time. The task is challenging since different vehicle identity of the same manufacturer, model, year, and color can look very similar. Moreover, for a given vehicle, its appearance and orientation can vary largely from camera to camera. To tackle this challenge, we propose the Ever model, which is composed of global local feature extraction and the key point-based attention module. For the Ever model, the upper phase is to retrieve the global vehicle appearance feature and embed the entire image into a 512-dimensional feature vector. We use L2 softmax, which is widely used in face verification tasks to train this module. And the train module can better separate vehicle identity on the surface of a hypersphere. This loss function compared to triplet loss is less computationally expensive and more stable without any requirement of applying hard sample mining. However, the global feature extraction module failed to capture the subtle difference between the vehicle of the same color, shape, and manufacturer in extreme cases. As shown in the sample images, those are vehicles sharing the same color, model, and the manufacturer. They can only be differentiated by focusing on rings and the tail light of the vehicles. To localize the region of vehicle containing discriminative information, we designed a 2-stage vehicle key point and orientation estimation network. The stage 1 is used for coarse estimation of vehicle key point location and is trained using pixel-wise cross entropy loss. In the second stage, the coarse heat map are refined and the orientation of the vehicle is also predicted. Here, we train the model using multi-task learning framework for better separation of undesired responses. The regression and the cross-entropy loads are used for heat map refinement and orientation classification, respectively. The reason for orientation prediction is that not all the key points provide discriminating information, and their contribution depends on the orientation. Thus, we define the orientation group to include most visible and related key points to capture these subtle differences of different vehicles robustly. Therefore, ever estimate the orientation, choose the best orientation group, and extract features in the local region of selected key points. We test the proposed approach on two main benchmarks for vehicle re-ID, Vari776 and the vehicle ID. We observe the proposed approach outperform the baseline model in all the evaluation particles and using across different architectures. We also compare the proposed model against other leading state-of-the-art method, and our method also perform better than this method for almost all the evaluation metrics across these two benchmarks. We find using the bench re-ranking in person re-ID also help to boost the NAP scores. Next, we also test the proposed approach on the most recent very wild and city flow re-ID dataset, and the proposed error model also outperformed the baseline on this dataset and show the effectiveness of proposed key point-based attention module. From the ablation study for the error model, we find the following factor help. Larger feature made from the earlier layer of global appearance space help to capture global information. Dual path feature extraction is beneficial to capture the subtle appearance variation of vehicles. Adaptive key point selection leads to better result. In conclusion, the two paths of error model help capture the global and localized discriminative features by focusing the attention on the most informative key points. We also open source the code for the vehicle key point and orientation estimation, and welcome to poster 17 for more detail and discussion. Thanks.
Good afternoon. My name is Zhiheng from Shanjiao University, and I'm glad to introduce our work, Bayesian laws on crowd counting. The target of this problem is to count the people in images. For labor saving, most of counting datasets are annotated with points. Directly regressing the point is difficult, so many previous methods transform it into a density regression problem. However, the true density is not available in this problem. The naive approach is to use Gaussian kernels to convolve the annotation points to generate a pseudo density, and then supervise a fully convolutional network pixel by pixel. Many previous work try to generate a better density for supervision, but our method is different from that. We do not generate any pseudo density for supervision and directly optimize the count. Here are the details. First, we construct a posterior probability from annotation points. Okay. Here's the detail. We construct a posterior probability from annotation points. The rule behind it is simple. The pixel has higher probability assigned to the closer annotation point, then the expectation count is calculated for each head by summing the product of probability and the output of the CNN. Finally, we can easily regress each expectation count to its target, which is available and apparently to be 1. It's worth to mention that we do not constrain density to any distribution. We introduce two assumptions for calculating the posterior probability. First, we set the prior to uniform distribution. Second, we set the likelihood to Gaussian distribution. Z is a position of annotation point, X is a position of pixels, and the sigma is set to constant. The final posterior formula is similar to softmax in classification problems. The differences between our method and the density regression are listed as follows. In summary, our method doesn't have to pre-generate a pseudo density for supervision and relaxes restrictions on density distribution to make the CNN model can learn an appropriate one by itself. For testing, there is no annotation point, so the posterior probability is not available. However, our target is to calculating the total count. By summing all the expected count together, we can marginalize the posterior probability. This is a visualization of our posterior with entropy. The higher entropy indicates the larger uncertainty of belongingness. The images show that the posteriors could find the boundary between persons roughly, and the crowded area has higher uncertainties than sparse areas, which is a useful property for handling the sphere occlusions in crowded areas. In previous formula, we only define foreground class which cannot handle pixel belonging to the background properly. By adding the background class and slightly modify the formula, we can get an improved addition. We name it Bayesian loss plus. The simple assumptions we use is that pixels far from any of the points should assign to the background. It can be seen that we only need to add an item to regress the expectation count of background to 0, and others remains the same to the Bayesian loss. Since there doesn't exist a certain background point, we introduce a dummy background point for each pixel, and the background likelihood is positively related to its distance from the nearest annotation point. The hyperparameter D controls the ratio between foreground and background. Then the derivation of posterior is just same as the original Bayesian loss. This is a visualization of density predicted by different methods. Compared with density regression, the density of our method is more concentrated in sparse area and more smooth in highly congested areas. We evaluate our method on 4 widely used crowd-counting dataset and all achieve state-of-the-art results. It's worth to mention that our method makes 15% improvement over the baseline on the largest dataset, UCF QNRF. The code has been released on the GitHub. Here is the URL and the QR code. Thanks for listening. Our poster is number 18.
Hello everyone, my name is Jinsong. Today I will present our work about learning spatial awareness to improve crowd counting. This work cooperates with Southwest Xiaofeng University, CMU, and MSRA. First, I will briefly introduce the aim of crowd counting. Looking at this slide, the input of the crowd counting model is an image with crowd people like this, and the output is a density map like the right figure. With these density maps, we can easily accurately estimate the number of people in the images. There are a number of successful previous works, but these methods are significantly tricky to learn spatial awareness in crowd counting. Here are 2 examples. We can see that the existing methods are unable to estimate the number, the size and the position of heads on high-density areas. Even more, there is a natural of mean zero noise in the low-density areas. After the extensive surveys, we find the main problem lies in the loss function. In previous works, L2 loss is widely used to compare difference of each pixels between the predicted density map and the ground truth density map. Since L2 loss struggles to retain the high frequency variance in the density map, it's unable to learn the spatial awareness. Compared with the L2 loss function, 10 years before, a well-known loss function named MESA loss was proposed to learn the spatial awareness. MESA loss is required to traverse all possible subregions to get the differences between the predicted density map and the ground truth. Finally, only the subregion with the maximum difference is selected for optimization. Unfortunately, although MESA loss is sensitive to the spatial awareness and robust to various noises, it cannot be directly used for existing CNN-based methods. Note that our work has explored a novel way to employ MESA loss for all CNN-based methods. This is a home framework of our spatial awareness. Note that our method is a multi-branch neural network. Then we will explain the details of each branch. First, the input images are fed into the backbone network to extract features and output the estimated density map. In each branch, the network is optimized with the ranking objective by sampling two patches. Here, one patch is a subpatch of the others, and then outputs a new density map. Then the updated density map are utilized to produce the subregion S1, which has high discrepancy to the ground truth. To facilitate the following optimization, the density values within the generated S1 will be erased in the next branch, and then repeat the operation like branch 1. After K branches, K subregions are fused to form the pixel-level subregion S, which is exploited to calculate the MEP loss. You can simply imagine that with these procedures, our method can optimize the pixels with different estimation errors. Generally speaking, you can consider our framework is an extension for the original MESA loss. We evaluate our method on UCSD, UCF CC50, World Explore, and Shanghai Tech datasets. Here are some representative examples of these datasets. And this is our experiment results. Our method significantly improves all baselines and outperforms the other state-of-the-art methods. And we also showcase the generated density maps of 4 examples from different methods. Our method has this contribution. We propose spatial awareness network and maximum access over pixels loss for addressing the issue of crowd counting. We provide the elegant views of what kind of spatial context should be exploited and how to effectively utilize such spatial awareness in crowd counting. And our method could be integrated into all CNN-based methods and is end-to-end trainable. Thank you. Welcome to our poster number 19.
Okay, let's now take questions for the 4 last speakers. Can I ask you please to stay with us a few more minutes in order not to make too much noise during the questions? So let's start from the audience. Are there any questions from the audience? Okay, maybe one question online for the first speaker. Typically, when you train a reinforcement learning model, you need a lot of examples. Can you comment on how you deal with that in your approach?
It's like you say about how to train the policy network?
Like on the number of samples you need to train with.
Actually, for the reported result in our paper, only annotates around 10 samples for each query anchors. Actually, we have to. Actually, we should not determine it in a fixed number, but for some reasons, we use it as fixed.
Okay. Okay. Thank you very much. Maybe a question for the second speaker. There's a question about the robustness of your model with respect to weather conditions and illumination variations, if you could answer that.
For this part, it will depend on the training data, and actually here is used to kind of the attention actually to help to discriminate the subtle difference. So if in order to handle this simulation, I think we need to other mechanism to handle that. But as compared to previous method, we show in our experiment that we can capture those local subtle difference. Yeah.
Okay, thank you. Maybe a question for the two last speakers, maybe a generic question, and I don't know who wants to answer. You both presented crowd counting approaches. Can you tell us a bit more about the biggest challenges that remain on that task? Maybe both of you want to share something?
So the biggest challenge, I think, is point annotation is a weak annotation. We lose shape information and scale information. So how to estimate the true density without this information, I think is still unsolved. And another challenge is adaptation between different data sets. The scale between different data sets is they have a large difference in scales. So how to train on one data set and adapt to another data set is still an open question.
Do you want to add anything to this, or you think it's good? It's up to you.
I think one of the biggest challenges is the scale variation, because maybe in all same pictures, because of the perspective, the people head size maybe some is very little, and some is very big. That is hard to handle the features.
Okay, thank you. Maybe let's thank all the speakers of this session. Thank you very much.